Today we are going to see interrupts in 8086. Question number 1 is what is interrupt? So your microprocessor is executing some program. Now you know that microprocessor is executing programs in sequence, right? During execution of the program, if some other device, input output device or by your instruction, something occurs so that you need to handle that particular operation, you go there, execute that part, and if you come back to your original code again, that is called interrupt. Let's take the example of practical life. I am teaching you right now. So I am the professor, I am doing my work, I am teaching you. Suddenly someone knock on the door here. Now this is interrupt for our regular teaching. Understand? So what I am supposed to, I need to stop my working over here, teaching over here. I need to go there, talk to him, discuss with him, close the door again. I will resume my teaching from where we have left. Understand? The same thing your processor need to do. This is called interrupt. Clear? Yes. Now, why interrupt is needed? Because with your microprocessor you can attach multiple input-output devices. Right? There may be keyboard, there may be mouse, there may be printer. Now, microprocessor can't go to each device and ask, would you like to do something? Would you like to do something? That is not possible practically. It is like I am asking each and every one of you. समझ पड़ी सुन out है समझ पड़ी सुन out. That is not the problem. What is the solution? You raise your hand. I am having a doubt. Ask the doubt, and I will solve that doubt. Understand? The same is your microprocessor is doing. Whenever keyboard is pressing some key, it will generate the interrupt. Microprocessor knows that there is an interrupt for a key. I will need to do something. Understand? Yes. So interrupts are heavily used inside your microprocessor, and they are a core of doing any sort of operation, because nowadays keyboard, mouse, screens all are very normal. Yes, they are there with your microprocessor. So every time your microprocessor need to handle interrupts. Clear? So to understand how interrupts work, what you need to do is very important. So we are going to study interrupts as far as 8086 is concerned. Done? Okay. Now in 8086, first of all, there are 256 interrupts in 8086. Out of that 256, they are naming like this IND, where n is your number ranging from 0 to 255. This many interrupts are possible. Understand? So in 8086, this many interrupts are available, 0 to 255, IND. IND is the instruction used to initiate your interrupt. Okay, so there are two kinds of interrupt. One is called software interrupt, one is called hardware interrupt. Okay, so if you as a user write down INT21H in your code, you are initiate the interrupt to stop your program. Yes, move AH, 4CH, INT21, you generate this interrupt to stop your code, right? So that is user defined interrupt. They are all software interrupts. Whatever user are defining are all software interrupts. In your 8086 chip, physically 8086 is a chip, right? It is a 40-pin chip. How many pins? 40 pin chip. For this chip, there are two specific pins assigned for interrupts. They are called NMI and INTR. These are the two hardware interrupts. So if I am attaching keyboard over here, the keyboard request goes to NMI and I need to handle it. Understand? That is my hardware interrupt. So if I am having input output device, I can attach them over these two pins. Clear? This one thing is okay. Now, what is the full form of NMI? The full form of NMI is non-maskable interrupt. It is non-maskable. What do you mean by that? In any situation, if something occurs on that pin, need to be handled by your microprocessor. Your microprocessor can't ignore that. If someone currently knock at the door, I can ignore it and I still teach you. That is possible. But something comes on NMI pin, you need to handle it. That is called non-maskable. A simple example is a phone call is actually maskable. Currently, I have put it on a aeroplane mode, so no call will come. I have make it disabled. Understand? But suppose there is an airbag in your car, and if you get stuck, it is called non-maskable. કંઈ પણ થાય આટલો ઇમ્પેક્ટ આવે આવું થાય તો એરબેગ ખુલવી જ જોઈએ, because it's a question of security. Understand? So there are situations where you require non-maskable interrupts which not get a which in any case not going to get masked. They are not maskable interrupts. They will get handled over here on NMIP. Understand? Same way, INTR is also hardware. So if mouse is attached over here, keyboard will be attached over here. It will send the request, it will come on INTR pin. INTR is normal interrupt which can be masked, it cannot be masked. It can be masked, it is depending on you, how you want to treat it. Understand? Yes. Now the question is, there are only two pins. There are chances that you want to connect more devices with your 8086 input output device. Then how you can accommodate more devices with your NMI and INTR? Only two pins are available. All other remaining are your software interrupts that you can write down in code. But what about hardware? Understand the problem? So if this is my microprocessor, okay, this is my USB, this is my NMI pin. I have connected one device over here. This is my INTR pin. I have connected one more device over here. But before this device, I can attach one more chip over here. It is called 8259 interrupt controller. Okay. So now in this interrupt controller, I can have more 8 pins. So now I can attach 8 different devices with my 8259. This 8259 is connected with INTR. So if keyboard is connected with this, it will send the signal. It will inform INTR that there is a request from some of the device. So INTR will ask over here, which device out of your 8 device? Understand? And it will tell it is keyboard. Understand? If you have attached printer over here, again request will go here. It will ask which device. It will tell printer. This address, the name is called vector. What is it called? Vector. Understand? So here there is no vector, it is fixed. Whatever is connected, you directly need to use it. But it is non-maskable, it is always gonna occur. Here it depends on you. You want to stop it, you can stop it. You want to execute it later, you can do that also. Understand? This is non-vector. So you can connect multiple devices with this. Get it? This is one chip which comes in your module number 6, interrupt controller. Why it is used? So that you can attach multiple devices with your single interrupt. Understand? Even here also, with this line you can attach 8259 again and you can do multitasking, multi-stage 8259 structure, so that you can attach multiple devices, more than a device if you would like to attach. Get it? Now, suppose two devices send the request simultaneously. Which one to handle first? Whom to give priority first? All that things done by 8259. So that if you learn 8259 properly, you can understand how it handles the interrupt. But this is the basic idea. Clear? Yes. What we have covered till now in 8086, there are 256 interrupts. There are two kinds of interrupt: software interrupt, hardware interrupt. Software interrupts are in the form of instructions that you are writing inside your code. Understand? Hardware interrupts are only two types. Only two pins are available: NMI, INTR. NMI is non-maskable interrupt which can't be masked. It always executes. And INTR is normal interrupt. Okay? With INTR, if you would like to attach more devices, you can use 8259 chip. 8259 chip can handle 8 different interrupts. Understand? Yes, this much stuff is over. Oh, good. Now, next, what your microprocessor do when interrupt occurs? That's the next question. Okay, so concentrate over here. This is my main program. Input segment. Yes, CS is pointing over here. Currently IP is pointing over here. CS and IP is my virtual. At this point, interrupt occurs. So at this point, when interrupts occur, my IP must be over here. Yes, because IP is always pointing to the next instruction to be fetched. Yes. So currently, suppose this instruction is in of the code which is predefined or it is defined by you as a user. So that code is called ISR, interrupt service routine. You need to execute ISR. It depends on which interrupts occur and you need to execute accordingly respective ISR. For keyboard the ISR is different. For printer the ISR is different. Understand? So based on requirement you need to execute different ISR, interrupt service routine. And when this code is completed you need to return them. Understand? This is what happens when the interrupts get generated. Clear? If you remember your basic subroutine example, call and macro. Remember, if I write down call SUB, what happens? You need to jump to the SUB. When IT statement comes, you need to come back to the next one. This is what you do. Yes, same thing happens over here also. But here, instead of RET, they are using IRET. Okay, now we need to understand why they are not simple RET statement, why it is IRET and what it actually do. So concentrate. First, it is a jump. Yes. So you want to go to location of ISR because it may be stored somewhere else. Yes. It is a code which is stored on some location. So you need to change your value of IP from current location to new location which pointing at ISR. Understand? You are going to change the value of IP. Now we already studied in call instruction that if you change the value of IP, you want to come back over here. This is a dynamic location. Yes, the interrupt can generate over here, interrupt can generate over here. At that time my IP will be pointing over here. So first time I need to come back here, I need to come back here. The address is not fixed. મારા પ્રોગ્રામમાં ઇન્ટરપ્ટ ત્યારે આવશે એ નક્કી નથી એટલે મારે પાછું ક્યાં આવવાનું એ જગ્યા ફિક્સ નથી. The location where I want to come back, the return address is not fixed, it is dynamic. Understand? Where I want to go, where I want to execute my code, that is fixed. Clear? What is not fixed? Where you want to come back. Yes, so you need to store the value before you jump so that you can come back on your current location. Yes, to store this location we are using stack and we simply push value of IP on my stack before I jump so that I am having the value of IP available with my stack. Understand? Yes. Now there is a concept called inter-segment jump, intra-segment jump. If you remember, what is intra-segment jump? Intra means same segment. So you are jumping into the same segment. If you are jumping in the same segment, your CS will remain same. The value of IP will get changed. Understand? But if you are jumping from one place to another place, and if it is inter-segment jump, then the value of CS is also get changed. IP is also getting changed. Understand? Yes. Now in 8086, all the ISRs which are available are of the nature inter-segment jump. What that means? Every time interrupts occur, you need to jump somewhere, and at that time you need to change the value of CS also, you need to change the value of IP also. Understand? So if I am changing the value of CS also, IP also, so before jumping I also need to store the value of CS also and IP also. Understand? Yes? This is okay? First task that you are supposed to do. What you need to do? You need to store the value of CS and IP on your stack currently. Okay, now again, there is a logical understanding. This is my stack. SP is a stack pointer, always pointing on the top location, right? Suppose here some data is stored. Now I want to store my CS and IP before I jump. Yes, officially stack grows in a opposite direction, negative direction. This is SP minus 1, SP minus 2, SP minus 3. This location is SP minus 4. Now stack is a part of your memory. Your memory can store only 8 bits of data at a time. Understand? IP is of 16 bits. CS is of 16 bit. 16 plus 16, 32. One location is of 8 bit. So how many locations needed? 4 locations needed of 8 bit to store my CS and IP. Yes. Now CS colon IP. Yes. Which one is higher byte? Which one is lower byte? CS is IP is low. Suppose 1, 2, 3, 4, 5, 6, 7, 8. These are the values. This is my CS value, this is my IP value. If this is my higher byte, in this also 1, 2 is higher, 3, 4 is low, 5, 6 is higher, 7, 8 is low. Understand? Now, higher byte stored at higher address, lower byte stored at lower address. Leader Indian rule, right? SP minus 1, SP minus 2. Which one is lower out of these two? Minus 2 is more lower. Minus 4 is more lower. Yes? So lowest value will be stored on IP minus 4. And the highest value will be stored on. So highest is CS. So first CS will get stored. Then IP will get stored. Even in this is higher value. So here X stored L, X, L. This will contain 1, 2, 3, 4, 5, 6, 7. This is how your data will get stored in state. Understand? Clear? Yes? Okay. We are not done yet. Concentrate. Now, so if I am currently on this location, interrupts occur, I need to find out the value of ISR where I need to jump. Before that, I need to push my CS and IP on stack. Done. I have pushed it. I am going there. I am executing this 9. Till now, everything is okay. By chance, here, this is interrupt. Now, this is not. Sometimes it is intentional. Sometimes it is unintentional. Right. By chance, this ISR is doing some add, subtract, or any logical operation, and it makes my carry flag equal to 1. And when I jump over here. Before that, my carry flag goes what to be 0. So actually in my code, I want my carry flag should be 0. But because that interrupt gets generated, when I go to ISR, now ISR has made my carry flag. So what happens when I come back from this ISR and come back over here? What happens? I am getting wrong flag. Understand? Yes. If I want to take some decision over here based on my carry flag, I will take wrong decision. There are chances. Yes? So when I come back to my original code, I want my original flag values again. Understand? Yes? So there are two things. First thing, when you want to jump, before that you also need to store your flag register on stack so that you can copy it there. So whatever is your flag register before your jump should be remain intact. Understand? Yes. Samajh padi? Before I jump over here, I want that all the values of flag should remain intact as it is. So when my ISR gets over, I want same flag values which I want before. Understand? So for that, your flag register is also stored inside your stack. Flag register is again of 16 bit, 8 bit, 8 bit, two locations. Understand? Yes? Okay, so concentrate. Whenever interrupts occur, what happens? First, your flag registers are stored inside your stack, 2 bytes. CS will store, IP will store. Total 6 bytes will get stored. Then you will fetch the value where you want to jump. You execute that code on return. Instead of now RET, here you are having IRET. Why IRET? Normal RET only pop 4 values. So it will only pop CS and IP. But you want to pop CS, IP and flag. It will pop 6 values. You can come back to the original location. Understand? Yes. This one thing is okay? Okay. Your microprocessor is doing one more task. After pushing flag inside your stack, it will make your TF and IF flag 0. What do you mean by this? TF is your trap flag, IF is your interrupt flag. What do you mean by that? When one interrupts occur, I don't want to handle another interrupt during that time. so it will make it stop. Understand? If I make IF equal to 0, your interrupt flag is disabled. Which interrupt flag is disabled? The interrupt which comes on INTR pin. Now nothing can come on INTR pin. Understand? When you are executing this. Clear? NMI is non-maskable, so if something occurs on NMI, it will occur. But you can stop at something on INTR. And what is trap flag? Trap flag is doing single stating. So when you want to jump over here, this code is written by programs. It is system program, right? It must be correct. Why you want to trace it? We don't want to trace it and waste our time. So there is no need to trace it. That's why we are making it 0 again. Understand? Yes. Let's repeat. When you are executing your code, interrupt occurs. What happens? First, flags will be stored on your stack. Second, IF and TF flag will become 0. Third, you will push your CS IP on stack. Done. Now you need to fetch new CS and IP. You want to go on your ISR, execute it. When IRT comes, it will pop the value from stack. It will come back to the original code. Clear? This much stuff is okay? Okay. Now there is a question. Okay. One more question. It is a saying that you can't mess with stack during your ISR. There is a nice saying that don't mess with your stack during your ISR. With stack, how many operations you can do? You can do only 2 operations. Push, pop. Understand? Suppose, by chance, in this ISR, there are 2 push operation and 1 pop operation. Okay, this is my stack. Concentrate. 1, 2, 3, 4, 5, 6. This is already filled by you. Flag, flag, CS, CS, IP, IP. Done. Now suppose there are 2 push operations, let us say 7, 8. And there is only 1 pop operation. This will go up. So now your stack contains 7, 6, 5, 4, 3, 2, 1. Now when IRT comes, what is the work of IRT? Simply pop first 6 values. You will pop, and this is not your correct flag, not your current location. You will reach to some different destination and your program gets stuck. Understand? So that's why number of push operation should be equal to number of pop operation during your ISR. You can't mess with your stack because it is used to come back to your original code. Understand? Yes. This one thing is okay. Now there is only one question remains. હમણાં સુધી આપણે જેટલું નક્કી કર્યું એ બધું ખબર પડી ગઈ. પ્રોગ્રામમાં ઇન્ટરપ્ટ આવે તો શું કરવાનું? ફ્લેગને નાખવાનો, CS નાખો, IP નાખો, નવી વેલ્યુ IF TF ફ્લેગને 0 કરો, CS અને IP ની વેલ્યુ શોધો નવી અને એ લોકેશન ઉપર જઈને ISR ને એક્ઝિક્યુટ કરો. જેવું ISR એક્ઝિક્યુટ થશે, આ એલિમેન્ટ પાછી 6 વેલ્યુ પોપ કરશે, you will be back to your main code. Yes? Now from where to find out the value of ISR? There are 256 ISR. એટલે 256 અલગ-અલગ ISR છે. For each interrupt there is a different ISR. Interrupt service routine. કીબોર્ડ હોય તેનો કોડ અલગ હશે, પ્રિન્ટરનો કોડ અલગ હશે. તો કીબોર્ડ છે તો કીબોર્ડનો ઇન્ટરપ્ટ ક્યાં છે? મને કેવી રીતે ખબર પડે? અન્ડરસ્ટેન્ડ? મારે મેમરીમાં ક્યાં જવાનું અને કયો કોડ એક્ઝિક્યુટ કરવાનો? That I need to check. Understand? Yes. So now the question is, how you can get to know that where your ISR is stored for particular interrupt? That is the question. So for that, in 8086, now concentrate properly. There is a table in 8086 memory. The table is called IVT, Interrupt Vector Table. What is the name? Interrupt Vector Table. It always start on location 00000H. So from the first location, your IVT will get started. Understand? Now it is going like this. INT0 is stored over this location. 1, 2, 3, 4. Now on this location, INT1 is stored. 2, 3, 4. Now this is INT 2. Now constant. This is INT 3. If I know the physical address, this is 0000, this is 00001, 2, 3, this is 4, 5, 6, 7, 8, 9, 10, 11, 12. Understand? Now, what is this? First of all, interrupt vector table. It is containing vector. What do you mean by vector? The address of my ISR. Your IVT is not containing ISR. Your IVT is containing the address of ISR. ISR is a code which is stored in memory. Where it is stored in memory, for that you need to go to first IVT table, find out the address and go to that address and execute your ISR. Understand? Executing ISR is a two-step process. First step, go to IVT table, find out the address, go to that address, now execute ISR. Understand? So your IVT table is containing addresses. Understand? Now we know that all ISR are stored in different segments. If it is stored in different segments, you need to change the value of CS, you need to change the value of IP. CS is of 16 bit, IP is of 16 bit. Total 32 bits are needed to know the location of ISR. Understand? That's why there are 4 locations required for each ISR. Understand? Address of each ISR. Yes? Yes? Constant. Here also this is normal memory where CS will be stored and where IP will be stored. Higher value up or down. 000 is lower than 0001. So higher value goes down, lower value goes up. So IPL, IPH, CSL, CSH. This is how your data will be stored. Understand? 3 is higher location, 0 is lower location. Understand? For 256 different interrupts, each interrupt is having 4 bytes of address, total 1024, 1K. So the size of your IP table is 1K. Understand? It starts with location 0000H. What it contains? Address where your ISR is stored. Understand? Now every time I can't go and check all my 1K locations. What is my address? So now if you will concentrate carefully, see, if I multiply this number with 4, I will get the starting location of my interrupt address. 0 into 4, 0. 1 into 4, 4. 2 into 4, 3 into 4, 12 is your C. Understand? Yes. Again. Now continue. Suppose here INT 2 occurs. Okay? Interrupt generated INT 2. What your microprocessor do? Push the flag, make the TF-IF 0, push CS, push IP, khatam. Now, because this is 2, multiply 2 with 4, you will get 8. You will come to this IVT 8, 9, 10, 11. Find out these 4 locations. Whatever number is stored on this location, suppose 1, 2, 3, 4, 1, 1, 1, 1. Go to this location. Here your ISR is stored. Execute this ISR, IRET. Go to your stack, pop the 6 values, come back to your original. Understand? This is what your microprocessor do every time. Understand? Yes. Suppose INT 4 is occurred. You need to tell me the procedure. What happens? I am running my code. My IP is over here. My interrupt generated over here. This is INT 4. What happens? First, push your flag on stack. Next, TF-IF 0. Next, CPIP push on stack. Next, this is 4. So multiply with 4. 4 4s are 16. Go to location 16. 16, 17, 18, 19. From this 4 location you will get CS and IP. that is your new CSN IP. Go to that location, execute ISR, IRT comes, pop these 6 values from your stack and you will get to your original code. Understand? Yes. This is what happens every time. Understand? This is how your interrupt work in 8086. IVT is not containing ISR. IVT is containing the address of ISR. Just keep in your mind. Done? Now the last one. This is my IVT. Okay? In IVT table, the first is I have 0, 1, 2, 3 and 4. They are already predefined and they are fixed. Interrupt 0 is divide error 0. So sometimes if you divide some number, if your answer is more than 8 bit, it will contain error. Then in that case, this interrupt will be generated and you can execute it. Understand? INT1 is single stepping that you are doing, graph layer. So if you want to do single stepping, the code of INT1 will get executed. INT2 is NMI. So something comes on pin number 2, ISR2 will get executed. Understand? Non-maskable interrupt. If something comes on that pin, this ISR will get executed. Whatever is on this location. Understand? 3 and 4. 3 is breakpoint. So if your code is very big, you know that this much part is okay, you can't put a breakpoint over there and then you can execute. Yes? So that kind of work can be done using INT3 and you can execute this ISR. And last is INT4. Overflow flag will get set when your answer is going beyond the range. We are already studying flag register, sign flag, overflow flag. So in that case also, this ISR will tell you that overflow occurs. Understand? 5 to 31 are reserved for future use. Okay? Interrupt INT5 to INT31 are reserved. And 32 to 255 are used by user. So you as a user can write down the code and you can write down your ISR. Understand? Yes. So this is your interrupt. Last and final time. This is my code, interrupt occurs. What happens? If interrupt occurs, you push your flag, then your TF-IF0, push your CS, push your IP. To fetch your CS IP, you go to IVT table. How you go to IVT table? Multiply your IVT with 4. You go to that table, find out 4 location, fetch that 4 location, that is a CS IP. Go to that location again, execute your ISR. When IRT comes, pop 6 values, you will be back to your original code. This is what happens. Understand? Done? And these are your basic interrupts. Clear? Thank you.